All right, so we're still talking about the reasons why you would need to start mechanical ventilation. And now we're just going to look at the high frequency. So kind of similar to what we were looking at when it comes to volume control versus pressure control with adults. You don't ordinarily start off with pressure control. You start off with volume control until they fail, and then you go into pressure control. With high frequency ventilation, it's kind of the same where you start off with a regular ventilator, which we'll just say conventional ventilation, and they got worse and you made all the adjustments you could and they still weren't really responding. And then you would now consider using high frequency ventilation. So that's our first criterion right there. Your patient failed low frequency ventilation or conventional ventilation. And I'll just write that in parentheses or at least here. And then another reason why you may want to right out of the gate consider using a high frequency oscillator or high frequency ventilation is if you already know in advance that there's going to possibly be some barotrauma issues if you use a regular ventilator, then you're going to use high frequency because as we'll see, the volumes that are being delivered with these types of machines are so tiny. They're considered to be your they're like what's the word I'm looking for, subanatomical. That's a word that we could use to kind of explain how small these volumes really are. You can't really measure them. The machine doesn't measure them. I don't believe the machine could even measure it if it wanted to. And there's certain disease states, so like, and again, like with RDS, some areas of the lung are going to inflate a little bit easier than others, which means that the areas that do inflate a little bit better are going to end up overinflating because of the other parts that don't want to inflate. So everything is going to be shifted and redirected to where it's easier to ventilate. So that's what they would consider like maybe using a high frequency for sure. And then number 3 is saying diffuse homogeneous lung disease. And I'm wondering if they really meant to say heterogeneous. Okay, but either way, just know that when it comes to like the baby version of ARDS, then we're usually thinking if they haven't gotten that bad yet, they're probably going to get a little bit worse. So we may as well just go ahead and consider doing high frequency ventilation. And then 4, with those air leak problems that we saw in chapter 22, like your pulmonary interstitial emphysema, and of course pneumothorax, you don't want to make matters worse. If there's already air leaking out, get them off of the conventional machine and then place them on one of these, which is going to still be able to ventilate, but using very small volumes and less chance of barotrauma. And then this pneumothorax here, we know that if you have an untreated pneumothorax, the last thing you want to do is place them on a positive pressure ventilator. But we're assuming here that the baby's already been treated. The baby's already got a chest tube in place. And now that the chest tube is in place, let's consider high frequency instead of just regular ventilator. All right, so the HFOV, and we'll get into it in the next few slides, which is, of course, the high frequency oscillatory ventilator. That is going to be the one that most hospitals are going to go to. This other one, the high frequency jet ventilator, it's still out there, but you probably won't really see it being used that often. And we'll see why. I mean, it's still an effective machine and it still can generate really, really, really high frequencies, but it's a little bit more troublesome and it's going to require a little bit more to get it set up and get it going and to manage it and things of that nature. But notice that they do have that the jet is going to be something. It's almost like a go-to if you've got a patient with a fistula, like in case like a bronchopleural fistula. And instead of doing the oscillatory or the high frequency oscillatory, then you may want to consider the high frequency jet ventilator instead. Now, this goes back to when we started looking at vent classification. And when it really comes down to it, the machine can really only control either volume, which would be volume control, or pressure, which is pressure control. These oscillators and jet ventilators, they don't do anything but pressure. So there's no tidal volume setting ever in these machines. It's always going to be some kind of pressure setting that we're setting. And then when it comes to pressure control or pressure ventilation, we know that we mostly are thinking about PPV, which is positive pressure ventilation, but there still is the iron lung and the chest cuirass that classifies as a negative pressure generator. And that's it. Those are only two options these days. They used to have some other devices back in the day that would generate negative pressure. It's kind of similar to like that chest cuirass. There was something that was called a pneumosuit, I think they called it, a pneumosuit, or what do they call it? I think it was a pneumosuit. And it was kind of like, place it on the thorax, and then it will somehow pull the air out, and then it'll create like a vacuum. I don't know exactly the work and the ins and outs of how it works, but it was way, way back in the day when they had that. And then the chest cuirass came out and was a much better alternative to that pneumosuit thing. All right, and then as far as if you had to do negative pressures, then so now think like, of course, a newborn or an older pediatric patient. If you really don't want to do any kind of artificial airways, because they may not need to be trached or intubated, then you'll just place them in like either like the chest cuirass or an iron lung. And as we know, there's the good and the bad when it comes to iron lungs or chest cuirass as far as what these machines are able to do. They can't do all the fancy stuff and the fancy modes that the positive pressure machines can do. I mean, you can't add PEEP and and things of that nature. You can't adjust FiO2 and etc. And then there's also a concern, is usually not that big of a deal when you have someone who's in an iron lung for a long time, because it's creating that negative vacuum inside between your body and the actual machine itself. It's pulling up on your body. So that way it pulls up on your chest and creates that pressure difference so that the air rushes into your airway. But as it's doing that over time, it's just constantly kind of like pulling up on your chest and then just releasing it. It kind of pulls the blood with it as well. So there's something that's called tank shock. So I'm just going to write that just as a side note here. We have first advantage of negative pressure is that you don't have to intubate and you don't have to worry about a trach. But I'm going to write here, but a disadvantage could be tank shock. So that's the thing. It's just that some patients will experience tank shock and others won't. It won't be necessarily much of a big deal. Now, pressure control, that's usually the name of the game when it comes to setting up the ventilator for these babies. You're gonna set them up in pressure control. And even some of the other older babies or the older children. So here we're setting the pressure, but what we're really setting is the delta P. So just to review what we talked about when it comes to pressure control, your actual pressure that you're setting, some of your physicians are going to order this value directly. They're going to want you to set the delta P at, say, like 20. And then you'll have some others that will say that they want the PIP to be 20 or 25. They just have to kind of do a quick review in your mind as far as PIP and delta P are not the same. They can be the same if there's no PEEP, but the minute that you have PEEP and with your settings, your PIP is now going to be higher than your delta P, because that's what delta P means. It's literally taking your PIP minus your baseline, which in this case will be PEEP. Yes, it's PIP minus PEEP. So that's why if you have PEEP, it's going to raise everything up with it if the lungs are like normal. I mean, really, really stiff lungs don't usually behave that way. It's not like a linear kind of fashion where as you go up on the PEEP, expect the PIP to go up by that much more. But with normal lungs, it kind of works out like that. So if you don't have any PEEP, PIP and the delta P will be the same number. So it won't be no big deal. I just remember having to kind of stop myself from time to time. Is different people, they had like different neonatologists that were rounding on these babies, and some of them would have their way of writing their orders, like they always write delta P, and others would write PIP. And so you always have to like make sure, like, hey, did you really mean PIP or did you mean delta P? And then they will say, oh yeah, I meant PIP. So that just meant that you had to adjust your delta P accordingly because the baby was on a certain amount of PEEP. And then of course you have to set your I time and your mandatory frequency. And if you need PEEP, of course, let me just add that PEEP. And then I'm going to write pressure support, but I'm going to put a little asterisk here. Because we know if you're doing pressure control SIMB, you can add pressure support. But if you're doing pressure control assist control, it's invalid. There's no pressure support that you can set in a mode that's not spontaneous, or a mode that does not allow spontaneous breaths to happen. Now the flow rate, your peak flow rate, I think back in Chang chapter, oh goodness, whatever chapter that was when we had our initial settings come up, and we were saying that for the flow rate, you like to start somewhere around 40 to 60 liters per minute, just to kind of get them started. In pressure control, there's no way that you can set your peak flow rate. The machine sets it automatically, and it changes. It will have to change from breath to breath sometimes because your lung mechanics will change. So if you didn't give the machine the ability to make those changes on the fly, like one breath, the peak flow may be, say, 8 liters per minute, but then the next breath, it might end up being 11 liters per minute. And then the next breath, it might go back to maybe like 9 liters per minute. So it just needs to have that control of flow. So that way it can still meet your requirements. Your requirements are the delta P, like make sure that the delta P is this, or make sure that the PIP is no more than this. And it will make those adjustments to the flow rate as it needs to ensure that that is your pressure limit, and you're not going to go any higher than that. So if anybody told you that you can set your flow rate directly in pressure control, they're lying to you, because there's just no way. So now, high frequency, here's another term here, HFPPV. And again, we've already established that when it comes to these high frequency ventilators, it's all pressure. There's no volume control, it's all pressure control. So really, you don't have to necessarily say HFPPV, because it's understood to be positive pressure, and that's it. It's not a negative pressure generator. It's not like an iron lung or a chest cuirass. And it's not like a volume control situation where you can set a total volume. It's all pressure control. And so here we have high frequency positive pressure ventilation. They're saying here 60 to 150 cycles per minute, which really means what it's really saying is that there's some manufacturers that will have a machine that's just dedicated for ventilating in this range, and that's it. So 60 to 150 cycles per minute, or hertz, is what that machine could be capable of doing. And it would be classified as just an HFPPV machine. But a high frequency jet ventilator can go anywhere from 240 to 660 hertz. No, I'm not going to say hertz, and these are just cycles per minute, because we'd have to actually divide this by 60 to get the true hertz. So let's just keep it at cycles per minute. So breaths per minute, 240 to 660 breaths per minute, or cycles per minute, is what your jet is capable of doing. And then the oscillator, or the high frequency oscillator machine, can do about 240 to about 900 breaths per minute, or cycles per minute. Now, what I included here was just an example of the most common model of high frequency oscillation, or high frequency oscillatory ventilation. And it's this machine. It looks like there's a lot going on with it, but really there's not much involved with this machine. Once you get the understanding, no, I wish we did. I really wish we did. At least my first job when I was in LA, we used to rent these machines. So that way, when we talked about high frequency, then we could use them, and you could set them up, and you can go through that whole process of calibration. No one really remembers the calibration process. So the manufacturer has literally, they've taped it to the top of the machine. So these are all your steps right here that you would have to follow. Kind of similar to like the ventilator in the lab, where it was telling you to go step by step to do something, and now do this, now do that. It's all written here, and you just kind of follow it. And then that way you'll be fine. These do not have the ability, as you see, there's no real computer brain. There's no like graphical user interface. There's no screen. There's no, touch. There's none of that, which means that everything is just, going to have to be either here on the top of the machine, or what a lot of hospitals will do is they'll have this same information printed out in like a little packet, or like a binder or something. And that way everyone will have a copy of it, or they'll hang it from the machine somewhere, just in case you forget. If you do enough calibration, you'll just have it committed to memory. But I don't remember too many people who would memorize this. They'd always go back to the top of the machine and follow the steps for calibrating. And so, yeah, these machines look kind of like, wow, what's going on? There's a lot, looks like there's a lot, but they really aren't. It's just a matter of getting familiarized with what's what. And then once you get familiarized with it, setup will be pretty easy. It has its own special circuit, as you see. This circuit doesn't look anything like the circuit that we're accustomed to seeing on the conventional ventilators. And as far as the settings, there's not many things that we're controlling. There's a few knobs here, and there's also not many alarms that you're going to be really trying to adjust. This is again high. This is like pressure, but high frequency. So our alarms are mostly going to be related to pressure. And then just as another, there's our blender. Our air O2 blender is right here. And that just means that your yellow and your green line will have to be connected to the wall. And it goes through this blender. And then you have to take your, it's not really clear on this picture here, but you'd have to take another tube and run it from your blender into your humidifier here. So this is how you're going to get your oxygen into the system. So as you see, this machine, after all these years, they still haven't designed it where it's just a knob that you turn and the machine will take care of all of this on the inside. So this is still, you got to set up yourself and just kind of connect it into the system, and that way you get the oxygen delivered that way. The machines in the lab, they have an internal blender system. You never see it. It's inside the machine. So that way when you connect it to the air in the wall and the O2 in the wall, it does all the blending that it needs to on the inside. So that way you set an FiO2 at 40%, it'll blend up the right amount of air and oxygen to deliver the 40%. And then as you see here, of course, you have to have humidification with this. There's no HME that you would ever use for one of these. It's gotta be heater. You gotta use heater with these. So there's of course our constant feed drain bag into our heater system. And then there's all these like color coded little connections here. There's a red one, here's a blue one, and then there's a green one. Now, if you read the machine, if you were actually at the machine and you could see exactly, it's going to tell you which one of these is which. You know, there's a white one as well. And these are going to correspond to these diaphragms mostly. Like there's a diaphragm here, which is like a little valve. They call it mushroom valve. And then there's one right here. And there's another one that you can't really see it right there. And then there's your temperature probe that will sense the airway temperature for the heater. So the heater will know what to do to turn up or turn down to maintain your target temperature that you have set. And this right here is really hard to see, but this is just like it's like a big syringe in a sense. It usually has like a little three-way stopcock on the end of it here. And this is kind of like our drain bag, if you want to think of it that way. Collects condensation here. So you just keep an eye on that, and when it gets to be about full, it's draining from here. This is called the diaphragm here. So once it's draining all of that liquid, you'll have to go in and then to take care of it and empty it out as needed. And what else is going on with this machine? Just from a surface, just overall looking at it. And by this little knob right here, I can tell exactly which model this is. They come in two different models. This company makes one that's called a 3100A and a 3100B. This has to be a 3100B because, no, this is a 3100A. I take that back. Because this little knob, we'll see it later, is what you're going to need to adjust to get everything to line up properly. Mostly it's the piston. This is how you're going to control the piston. And you can't see the piston. If you took this off and then you pulled that little black diaphragm away, on the other side of that is where the piston is going to be. And this knob is how you're going to get it to center, as they say. And if it's not centered, if the piston is like off center for whatever reason, the machine is not going to run at all. You're going to have to recenter it and then get it to start up again. It's kind of neat as far as like when you trying to get this thing to start up, almost like trying to start some kind of fancy car, but everything isn't really set up correctly yet, so it's not going to start. It's not going to crank. And then once you get everything lined up, then it takes off with no problem. Okay. So again, another thing about this machine is it uses a lot of gas. So if you're going to be using, like when we were doing it at my first job, when we would have one of these in the lab and we would connect it to like an 8-cylinder, it pretty much drained that 8-cylinder in just a matter of minutes because it uses a lot of gas. And you'll see why. I mean, because this thing, as you see, is generating like anywhere from like 240 to 900 breaths per minute or cycles per minute. And then that piston is going to need that gas to make sure that, you know, it's moving like it's supposed to. So now when it comes to your airway, you don't have to have any special airway to use a high frequency oscillator or a high frequency jet ventilator. Well, no, let me say oscillator, because we'll see with the jet, you are going to have a special airway. But with the oscillator, your patient is just going to still the same 15 millimeter adapter connection. So that doesn't change. Even though the end of this tube doesn't look like it, there's a little green stopper there. It doesn't look like it, but that will fit a standard ET tube adapter with no problem. And you can directly control your mean airway pressure. And let me just write here MAP, because we have to think about context. If you're looking at something related to ventilator settings and it's an oscillator, if you see MAP, chances are they're talking about mean airway pressure, not mean arterial pressure. But if you're looking at some vital signs and you see something related to blood pressure, or you see something that says MAP, then you know that that has to be mean arterial pressure. So it's just unfortunate that we have these abbreviations or acronyms that will kind of like translate to different things, but that's the whole point of like putting everything into context. Just like with BS, if we're talking about assessment of the lungs, then we know that if our abbreviation of BS is breath sounds. But if you're doing something related to the GI system, you're checking to see if there's any sounds in there and there's any gas moving around, then BS stands for bowel sounds, and so forth and so forth. So that's why, again, we know what we're talking about if we have everything else kind of talking about the same thing. But I still will just put it there just so that we know we're going to go back and forth. I try to just write it out as MPAW, but sometimes it's not even written as MPAW. It may just have the PAW, which is airway pressure with the line over it, which means average or mean. Now, your delta P on this machine is going to be controlled by what's called the amps or amplitude. That's kind of like your tidal volume, but we know that this is not volume control. You're not setting a tidal volume, but similar to pressure control, if you're increasing your pressure, you should get more volume, and vice versa. If you're decreasing your pressure, then you should get lesser volume. But we're not really going to be able to measure those volumes, but we do know that a higher amplitude would mean more volume underneath the curve, and vice versa. And then what's making all that racket, because these machines are loud, what's making all that racket is this piston that's moving back and forth. And that's what's going to be delivering the high frequency breaths. So it's not really like a conventional ventilator where you slowly get a breath delivered to you, your lungs inflate, and then the machine will stop the flow and allow your lungs to just naturally deflate and recoil back. With this machine, that piston is literally pushing air or gas forward, and it's pulling back as well. So it's an active inspiration and it's an active expiration. So that's definitely one of the other main differences between this type of machine versus, say, like a regular ventilator. Regular ventilator, there's active inspiration and passive exhalation. But with this machine, it's active everything. It's active inspiration and it's active expiration. It's pulling the gas right back out as the piston goes backward. Okay, and I guess while I'm here, just again, I mentioned that I was looking at the knob here and I said, well, this has got to be the 3100A model versus the 3100B. The 3100A is going to be reserved. The company that makes this machine, they publish their requirements as far as or your patient requirements, saying that if you have a patient less than 35 kilograms, then the 3100A is going to work out just fine. But if they're larger than 35 kilograms, that's where the 3100A is no longer going to be effective, because you're going to have to go to the B model. So that means that with the B model, you could ventilate babies or adults. But with the 3100A model, you can only ventilate like the babies and the smaller kids. You can't really do much with the adults with that. And all it comes down to its maximum settings that can be achieved is what it really comes down to. Now, of course, they started with the A model first, and then they went back and did the B model. But they still have both available. So sometimes hospitals will have, I've seen this happen before, they will have nothing but 3100A models in the nursery. And then if they were going to be using this on an adult every once in a while, they would have a couple of the B models as well. So that way the adult ICUs could have it. Oh, and I forgot to kind of just point out something else. This is how we're turning the thing on and off. So it just really comes down to flipping the switch here to get it to turn on and turn off. And then I guess while I'm here as well, I mentioned that this is, of course, our air and O2 blender that's that's connected here on the outside of the machine. If you turn your blender to 40%, these knobs are getting turned all the time. They're getting turned higher value, and then they're getting turned back down to a lower value. Over time, any machine where you're turning a knob constantly or all the time, one way, one direction or the other direction, you start to get, you get to a point where things are slightly off. So your dial is pointing to 40, but the inner workings or the interior components have probably shifted a little bit, or the dial itself has now shifted on that bolt that is bolted to. And either way, you can't really trust these things. Don't look at one of these and say, I know that my patient is receiving 40% because that's what it's pointing to right now. You're going to have to use an O2 analyzer. You got to with this machine, because it doesn't have a built-in one internally like the other machines do. So once your O2 analyzer is set up, you'll have to connect it in line somewhere as well. Usually it'd be somewhere like here on the heater, like where the circuit is connected to the heater. And then that way, if the analyzer is telling you that the FiO2 that it's measuring is about 35%, you're going to have to turn this dial up even higher than 40 until the analyzer is reading about 40%. So again, when you're documenting, you're going to be documenting FiO2 based on your analyzer, not the actual device itself. How does some companies kind of get around that problem with knobs that kind of get off center a little bit over time as you're constantly turning them? Some companies, especially like the ones that make transport vents, they have, I don't know exactly how it works, but they'll tell you that you're supposed to, after so many times of use, I mean, however many times you've used the device, you should take all the knobs and just turn them to their max and turn them back to their minimum settings and just do that a few times. And then that way it will help to, I guess, recalibrate and get everything lined up again. Again, I don't know exactly how that works, whether it's using some kind of like spring kind of mechanism or whatever the case may be. But in other situations, you're probably not going to be that concerned because you're always going to be using, like, especially like with an air O2 blender system, you're going to be using an O2 analyzer. And again, that goes for any situation in a nursery. If you're using a blender, you're going to also need to have an O2 analyzer that is telling you exactly how much FiO2 this system is delivering you, not what's on the dial. Okay, and so here is a close-up. So we got a closer look, and this is the Model A, as you can see over here. These companies, they've changed owners many times. I mean, we still say it's the Sensormedics 3100A, but the company now is Bias. They're the ones who bought out. And then I think at one point CareFusion bought this company. But either way, that's not here or there. It's just that this is still the same machine, more or less, and it does what it's supposed to do. And so this is what I was trying to come up with. I was trying to say sub-anatomical. I was trying to say like really small volumes. Really, we're saying less than your dead space volume. So whatever your dead space volume is, these little breaths are going to be way smaller than that. Ordinarily, if you're delivering a breath, like say your dead space volume is 50 milliliters, and your volume that's being delivered is only about 20. And you already see the problem with that. The 20 that you're delivering is not going to do any kind of gas exchange whatsoever because your dead space volume is 50. So with this machine, we're going to have to look at how it really is set up so that way the baby still will be ventilated, even though these volumes that are being delivered are so tiny. And then our ranges. So here we have it in hertz. So in the previous slide, it was talking about cycles per minute as far as the capabilities of the different types of high frequency machines. And as you know, when it comes to hertz is like 60 cycles in 1 hertz. So if you multiply 60 times 4, then that will tell you that it could range anywhere from about 240 cycles per minute or breaths per minute, and then 15 times 60, which will be your 900 cycles per minute. All right, so here we have, again, not much going on. Here's your mean pressure monitor. And why they include a positive sign here, I'm not sure, because there's really no situation where your pressure is going to be negative, like your mean airway pressure is going to be -10. But maybe it's one of those things where it could be helpful for troubleshooting. And then this little LED right here is like 3 little LEDs. Here is center, that's the center position. This is the piston's position. So you can see at any given time what the piston is doing. As long as this, as long as it starts in center, and it'll just literally, it'll just go back and forth at a rate of like either 240 cycles per minute or 900 cycles per minute based on your Hertz setting. And then right below here is, of course, your start stop button. Sometimes you're gonna have to stop this machine so that you can assess your patient. There's no way you can hear breath sounds with this machine going at the same time. So in those situations where you do have to do an assessment and your baby is on the oscillator, you're gonna have to temporarily hit the stop button. But you don't wanna keep it stopped for too long, especially if this is a critically ill baby. And then over here, this is our amplitude. So this is like our delta P. Or amps, as they call it. This will be a setting that the physician will have to give to you and say, let's do a delta P, let's just make it like 20. So delta P of 20. You see this and you'll say, okay, that looks to be pretty good, because it's hard to kind of get this machine to stay on whatever it is that you set your delta P to. And you'll make adjustments as you need to, so that way it's not too far off. But this is not too far away from 20, so that's why I just used the number 20 as an example. How you're achieving your amps is this knob right here. It's called the power. It says power, and that's all it really says. And the numbers on here don't really mean anything. They're there, but you're not going to document it, because you're going to just adjust this knob until you get your delta P to be what it is that you're trying to get. And then over to the side, it's hard to tell, but there's like a little mechanism that will lock it in place. It's almost like to me, it looks like a combination lock. When you're turning the little knob on the combination lock and you're seeing the numbers go by, you'll see the numbers in this little window here. And then because this moves so easily, it's so easy to make this little knob move. And then they include this little locking mechanism. So that way, after you're done setting it, lock it in place, because this machine is vibrating. It's moving, especially if it's moving at 900 cycles per minute. It's moving so much, and it's moving, it's bouncing, it's vibrating. That's enough to jar that power knob if it wasn't locked, and it could change your amp setting without you even knowing it. Just another side story or side joke. I remember a lot of ours, the locking mechanism wasn't even working anymore, it was broken. So that meant we were having to constantly go back and check to make sure that the number didn't fluctuate too much from what we had set. And then here, this is our I time. So this is how we're setting our ID ratio. Oh, percent I time. This is our percent I time. In most cases, they're going to just want you to do an ID ratio like 1 to 2. Again, unless you're dealing with some patients who are really, really, really bad, like a really bad case of RDS, then they may want you to target like maybe like a different ID ratio. But in most cases, they're going to just expect you to just keep that ID ratio at 1 to 2. If you don't remember how to calculate percent I time, the shortcut for determining ID ratio when it comes to percent I time is to take this number. This is 33% I time. How many times will that go into 100? Approximately. That'll approximately go into 100 3 times. You'll end up with like 99. So 3 equal parts that represent 99. I'm sorry, that represent 33. And then if you take one of those parts out of that whole, you got 2 left over. So that's your 1 to 2 ratio. that you set based on your percent idle time. And then for whatever reason, if you needed to have like a 1-to-3 ratio, you're going to have to set your percent idle time to, and again, this probably would never ever happen with a newborn, but right, you'd have to set it at 25%. And then here, this is how we're setting our hertz. So this is our frequency, which is our hertz. And as we briefly seen, it came up, I think, in one of the chapters when we were talking about band classification or modes or whatever the case. I think it was modes. This is kind of opposite of what we normally would think about frequency. Ordinarily, like on a conventional ventilator, when your CO2 is too high, you would have to end up increasing your frequency. So that way you blow off more CO2. But with this machine, it works differently. If your CO2 is too high, you're gonna have to decrease your hertz. And if your CO2 is too low, you're gonna have to increase your hertz. And then we'll see the rationale behind that when we start looking at the graphs or the waveform that represents what's going on with each cycle. And then over here, of course, these are the knobs that control. And then over here, we've got, it says mean pressure in this little category. You notice how they've got things kind of like sectioned off. So that's why I started here and then I jumped over here. I was going to save alarms to last anyway. So they've got their own little sections on the panel here. So now we're here at the mean pressure. It says limit, and it goes anywhere from like 10 to 45. And there's no values per se that you see printed on the panel itself. It just says min and then max on this side. And then it says here, adjust bias flow dependent, which means that there's two parameters here, two settings here that can make, if you change one, it might affect the other. And then right here, there's the knob there. So adjust with this and this right here. These two, if you adjust your bias flow this way, then you may have to change this, which is just called the bias flow. It looks kind of like a flow meter, and that's essentially all it is. There's our little floating ball that will represent how many liters per minute of flow. And in most cases, you're going to usually start around 20 liters per minute of bias flow. Bias flow is the way that CO2 is going to, for sure, get flushed out of the airways. Being that we're delivering such tiny, tiny, tiny little volumes, which really aren't going to help with ventilation per se, the bias flow is going to be like that fresh air that they'll be getting at a rate of like again, maybe start like 20 liters per minute. And then you could adjust your bias flow as needed. And then again, if you didn't want to do it this way, you could just use this knob to adjust your bias flow. And then back over to here, here's our alarm. So not very sophisticated at all. Here's a high pressure alarm, and here is a low pressure alarm. And this is our silence. So when the machine starts alarming, here's how you silence it for a couple of minutes. And then this is the reset, which means that if the piston jumped off center for whatever reason and the machine stops, once you get the piston recentered, then you hit this reset button or reset power fail button, and then you hit the start, and then it'll start up again. But if that piston is not centered, I'm here to tell you, you're going to be sweating to try to get this machine to start up again. And then down here, it's just some warning lights, you know, as you see color coded. These are red, which are high priority because they're related to like your power fail, like the machine the thing just stopped because maybe it overheated and it stopped. And then these, of course, are like your alarms, like you've got a high pressure alarm set at 25 and a low at 5. then you want to know if something happens and the pressures end up being higher than 25 or lower than 5. And then down here, so these yellows are kind of like, definitely still an alarm situation, but maybe not as high priority. And that could be, something related to the internal battery that it has. That's an alarm that will go off. And then there's the overheat. Like this thing is getting too hot and it's just switches off. That probably should be like a red high priority kind of alarm, if you ask me. And et cetera. So again, not much really going on, but at the first time using it, it could be maybe a little bit overwhelming as far as like, what is it that I'm trying to do exactly with this machine and how am I making my adjustments? Okay, so now here is what we know. We know that when it comes to hertz, there's 60 cycles in 1 hertz. So in other words, 1 cycle per second. So we got a case of like 10 hertz, that would be 6 times, that would be 10 times 60, which is 600 cycles per minute, or 600 breaths per minute. The graph here is trying to show the main difference between, say, just regular like ventilator and patients in pressure control, which is the graph here, or the tracing here. This is pressure time graph. And then this is the up and down, up and down, up and down. These are those little tiny breaths that are being generated by the high frequency oscillator. So they place them both on the same picture here just to kind of have a compare both at the same time. Now with the regular ventilator, baby's in pressure control. So what do we know from this graph? We know that this is 0. There's a PEEP of 10 that we have set. That's our baseline pressure. And our pressure control is set at 30. So our delta P in this example looks to be 30. And the peak pressure, maybe it's a little bit more because this is 40 and that's the peak right here. So it's a little bit more than 40. But I'm just gonna rough estimate this to say the PIP is about 40. So that would mean that if the PIP is about 40, the delta P is 30. We set the delta P to be 30. So I see 35, but remember, delta P is or baseline. So our PIP is about 40-ish. It's a little bit more, but I'm going to just say 40. Our P is 10. Yeah, notice what I'm saying. It could be maybe 45, in which case it would be 35. But again, maybe. So it'll work either way. If you estimated this to be about 45 PIP, delta P would be 35. But I was just trying to make it easy for my eyes and just say, I see 40 right here. So let's just say it's pretty close to 40. Now, the graph here is, again, look at how your baseline pressure is. There's no peak per se when it comes to high frequency ventilation. So you're not setting like a PEEP of 5 or a PEEP of 10. It's really going to be all dependent on just overall mean airway pressures. So mean airway pressure, first of all, for the conventional ventilator, looks to be about 25. Mean pause about 25 in that example. But notice that with the high frequency, that's like our baseline. And we go from about 25 to about almost close to maybe a little bit more than 35 to almost, heading toward 40. And we just go back and forth from there, which means that overall your mean airway pressure, and this is under your control, you set the mean PAW in high frequency ventilation. So that's set at about 30 here. Okay, so this will be the last thing that we do for today. Just take a look at this video here and see. This is just an example of just one hospital and their policy as far as high frequency ventilation, what they do. And it's a good illustration to show you the main things that you need to be focusing on when it comes to the settings on this machine here. So let me take,
The high-frequency oscillatory ventilator by Dr. John Arnold. Please note that in this video, we will be following the guidelines used at Boston Children's Hospital. Some of this information may need to be modified based on the equipment, guidelines, and practices in place in your institution.
I'd like to take several minutes to demystify this device. This is a high-frequency oscillatory ventilator, as you know. This is the Sensormedics 3100A. And when initially confronted with this device in the ICU setting, many people are confused. Let me help. This is simple. This is the mean airway pressure, and you're familiar with that number from conventional ventilation. And this is the amplitude. This is the delta pressure, measured proximally in the ventilator circuit. These are really the only two numbers you need to concern yourself with. When we transition to high frequency, almost all patients are on 100% oxygen. We typically will pick a frequency based on the patient's size. And Samantha, a 13-month-old, roughly 8 kilogram child, we're going to pick a frequency of 10 hertz. And virtually all of our patients are managed with an I to E ratio of 1 to 2, giving a percent inspiratory time of 33%. So we're going to ignore these two numbers and focus on these two. So as you know, when we transition to high frequency, we will typically transition at a mean airway pressure 5 to 8 centimeters higher than we were on conventional. And one typically sets up the ventilator prior to transition. Now you can increase the mean airway pressure knob in one of two ways. You can adjust mean airway pressure by manipulating the size of the orifice on the expiratory limb, which is what I do when I manipulate this knob. So I'm increasing mean airway pressure and I'm decreasing mean airway pressure. And the other way to manipulate mean airway pressure is to increase the flow through the circuit, through that fixed orifice. And that's called the bias flow. And we can do that by manipulating this knob. All patients need to start with a bias flow of 20 liters per minute. Occasionally, when you've increased mean airway pressure maximally by closing the orifice, you will need to increase the bias flow to further increase the mean. So I'm going to now increase the bias flow from 20 to 25 to 30 liters per minute. And look what it's done to the mean airway pressure. It's increased it dramatically. Let me go back to 20 and you'll see that in reverse. 25 and 20. So that's mean airway pressure. Now the delta pressure is displayed here. It turns out we adjust the delta pressure by turning the power knob. So you actually increase power, and that generates a higher delta pressure, which is a measured variable. And we increase power simply by turning this knob. So I'm now aiming to increase the delta P to 60 by increasing power. The delta P is the peak to trough pressure, again measured proximally in the ventilator circuit. And to increase it further to 65, we simply increase power in another increment. So very simple device. The conventional ventilator is complicated. This is not. We focus on mean airway pressure and delta pressure. I hope that was helpful.
That concludes our video on the high-frequency oscillatory ventilator. Thank you. Please help us improve the content by providing.
Okay, all right, so it was short and sweet, and I think it hit the major points that we are focused on when it comes to these machines. And again, I'm just going to leave this for Thursday, the rest of this for Thursday, and we can finish that off, and then we'll still have plenty enough time to take care of the information that's in the chapter on CPAP and non-invasive, which is I think 15 and 16. Okay, so that's all that we have for today.